Hello, and welcome to episode number 24 of CS350 Online. I'm your host, Leslie, and today is our last episode. This is your last day of classes, for us at least. So, what are we going to do today? So I thought we'd have a little bit of fun. First, we're going to take up my favorite sample problem that we have, which is going to be computing the number of reads and writes which happen given that little snippet of code that we had before. And then after that, we're going to talk about how to design an operating system and all of the different things that you would need to consider in order to design an operating system. Because I think it's both a good review of the topics that we've learned so far, and it also gives you a little bit of room to think about, if you had time, how would you do it? And I mean, what I can say here is that when I was a kid, there were three big things that every person into computing wanted to do. Ray tracer? Okay. Did that. I'm in graphics. Write lots of them. There was a compiler. I've scored that one off my list. The other thing was everybody wanted to make their own OS. And that is the one thing I have not done yet, is made my own OS. Someday. All right. So, but first, of course, we want to talk about our OS of the day, and I have saved the best for last. So, OS of the day is Temple OS, and many of you probably guessed I was saving this to the very end. Indeed, I was saving it. Now, there's lots to be said about Temple OS. It is a bit of a controversial operating system, but it's also a technically interesting operating system, which is why I've included in this deck. So first off, this operating system was released in 2013 by an individual by the name of Terry Davis. Now, some of you may have heard of this individual, and others of you may not have heard of him. Regardless, I wouldn't recommend that you look up his YouTube videos. He was a rather opinionated individual and may not have had many politically correct opinions, and was known to have ranted about said opinions on YouTube, pretty much offending everybody in sight. But he has a story. So he was actually a software developer who was once upon a time atheist, but he also suffered from manic depression, as many individuals do. And he had been through several institutions. And my understanding is that during one of his institutionalizations, that's a big word, he had a dream or a vision or an episode where he believes that God came to him and told him to make an operating system that would be God's official temple. Now, I'm not going to sit here and argue whether this happened or not, because we'll never know. And that's the truth, we will never know. But this is the story of how the OS was actually created. And so Terry Davis actually set out and created this operating system in God's image. Again, that's how the story goes. So you'll notice I refer to him in the past tense, and that's because I think it was a year or two ago he was hit by a train and actually killed. And it's not clear whether it was an accident or whether it wasn't, but nobody wishes death on anybody, so regardless of their state. So it is a bit of a tragedy here. The operating system, though, let's talk about it, is actually quite interesting. So it has a 640 by 480 screen. It has a point-and-click based desktop environment with 16 colors and one audio voice. And the reason why these are one audio voice is because it is supposed to be the voice of God. And you shouldn't have multiple audio voices, because that would be portraying multiple idols, which is not the goal of the OS. It has no support for networks, or at least it originally did not. And here's where things start to get very interesting. There is no separation between user and kernel privilege. Everything, including the user programs, are running in kernel privilege. Now, you might be thinking to yourself, oh no, what's going to happen? But actually, let's think about this for a minute, because this is why this OS is interesting, is because it has some technical quirks that make it an interesting discussion point. Let's imagine that every program ran with kernel privilege. Your operating system would actually be blissfully simple. So you can actually go and download the source code to this. It's open source, it's free. And you can actually see what has been done to it. And you can see that because you don't have the system call interface, it's actually blissfully simple code because the user programs can just access the data structures. They can just call the API functions. They don't actually need to raise exceptions and go through that whole process. So not only is the code base simpler in the absence of system calls, but it's also faster, because we don't have to raise exceptions and wait for them to be handled. So all of that work that we do in any modern real operating system, not to say that Temple OS isn't a real OS, because it is, but nobody uses it, of course. It's going to be faster because there's no system calls and all of those stack frames. We don't have to deal with that. So there's one really interesting design decision that was made for this OS. And then here's another one. There's one address space. So all of the processes actually are sharing an address space, which means that they can easily communicate with each other. So we don't need to do anything like IPC, which is inter-process communication. So things like message passing, UIs, we don't need to do shared memory mechanisms. They can just directly communicate with each other, which has advantages, again, of performance and working together. Disadvantages, of course, are that it's not very secure and that race conditions can happen, and you've got to be very careful about that. But this was perceived as being okay for Temple OS because why would you do anything bad to God's temple? So it's interesting design decisions from a technical perspective, and you can kind of justify where they came from based on the origins of the OS. As I said, this is kind of a quirky OS. Now, aside from that, Temple OS does have fully preemptive concurrent multi-core support. So this operating system, even though it has a lot of restrictions in the screen size and screen colors and the audio, voice, and new network and things like that, it also has a lot of features that we anticipate in a proper operating system. So it is a very limited operating system. It is very much like a Commodore 64 OS, if you've ever seen a Commodore 64, and it is very much biblically themed, as we will see in a moment. He also wrote his own file system for this, and the file system is called the Red Sea. The Red Sea, I mean, you part the Red Sea, you partition a file system, you part the Red Sea. So he made his own file system. He wrote the operating system. It wasn't good enough to write it in C, so he actually developed his own language called Holy C, which is a variant of the C language. And that actually has many of its own quirks. And I used to actually, and I don't have it here, let me just search. I had one point actually looked up what Holy See looked like, and it had some really interesting quirks of its own. I think something about not having to declare variable types or something. It's interesting. You should look it up if you're curious. And so Temple OS was actually written in Holy See. So a couple more comments on Twitch. So this is all under the assumption that the user program will never do something stupid. Yeah. Yes, exactly. So one of the consequences of these design decisions, like having one shared address space and everything running kernel privilege mode, is that you really are making the assumption that nobody is going to write bad programs and nobody is going to write malicious programs. But if you think about the origins of Temple OS, it's very easy to think that Mr. Davis had the thought that why would anybody do that to the temple? So there you go. Now, it had some other things, like it had an oracle that let you communicate with God and various other things. So I actually have a screenshot of it here, and you can go on YouTube and watch people use it. So what you can see here is it's actually interacting with a Windows file system. It's presenting itself as that. Down below here, you can actually see all the different operations going on. So the memory reads and writes, the disk operations. It's kind of neat, right? Because everything, is running in kernel mode. You have access to all of that kernel information right off the top. And so some of the programs he has, you can see he's got some games. So he's got The Dead and Strut and Bomber Golf. He was very much a gun enthusiast, is my understanding. And on Twitch, somebody commented that it had a flight simulator. I'm sure it did. It also has a bunch of biblically themed programs like Wenceslas, and instead of calling the keyboard, a keyboard, he calls it psalmody. and things like that. So that is Temple OS. And again, you can actually go online. You can download the code for this. You can see just how different an OS would be if we didn't have system calls. And you can give it a try for yourself. There's instructions online for how to run this in a virtual machine. Have some fun. I mean, if you're really bored, I mean, you've got like a week or so before I think the final exam will become available. So, you know, have some fun. Try out random OSs. It's like when, you know, there's this old saying, oh, when you go to college, you go to university, that's where you're going to try all the, you know, the debauchery, all the different drugs and stuff. Instead, you could just try all the different operating systems. Another comment on Twitch. I would have not have guessed this was created in 2013 based on the screenshot. My understanding is that the vision that Terry Davis had from God stated that this had to be the screen resolution and the colors. I don't know. I mean, I could think of some reasons why that might have been the case, but if we're thinking about this from a, hey, this is a modern operating system, when I look at this, it makes my eyes hurt. All right. But then again, you know, all my monitors are 4K, so. All right. So that is the end of those. And I would now like to go and talk about our last sample problem. So I am going to bring it up here. For those of you following along at home, this is the file I/O problem. So we have a very, very large file. You can assume it's something like 4 terabytes in size. It's just enormous. And we have a buffer that stores 1,000 bytes. And I am going to seek to byte 10,500 of the file. And then I am going to write 1,000 bytes and then read 1,000 bytes. And then we'll be done, right? And we're going to assume that our block cache and our inode cache are initially empty. And I want to know how many reads and writes actually happen on the disk. So let's actually start to figure this problem out. So let's open up OneNote. Maybe it'll cooperate today. Probably not. There you go, some nice lines. All right, so the first thing that you need to do before you can count the number of reads and writes is you actually need to figure out how is this inode organizing data? So we have a file system that is using 1,024 byte blocks, so 1 kilobyte blocks. And our inode has 9 direct pointers, 1 indirect, and 1 double indirect pointer. So in order to figure out how many reads and writes there are, we need to know through which pointer can we access byte 10,500, 11,500, and 12,500, and 13,500. So we need to know where those blocks live. So we're going to start by evaluating the direct pointers. So let's take a look here. My mouse is on the wrong screen again. Okay. So first we have 9, helps if I have a pen here, 9 direct pointers. Each direct pointer is pointing to 1 block of data, which means that the 9 direct pointers point to the first 9 kilobytes. So that's going to give us 9 kilobytes of data. So it's going to look something like from byte 0 to, let's grab a calculator here. I always forget to write down the calculations. So let's do 9 times 1024 equals 9216. There we go. So these are the bytes that are accessible via the direct pointers. And we are after byte 10,500, so we haven't actually found our data yet. So now, before we investigate the direct or the indirect pointers, we need to actually figure out how many pointers fit into a pointer block here. Whenever you see that the pointer size hasn't been specified, you should assume that the pointer size is 4 kilobytes. That's very standard. So let's figure out the number of pointers per block. And the math for this, again, is posted on Piazza in the disk drive math, or the file system math guide. So the number of pointers per block is, we're going to take, that is 1 kilobyte, which is 2 to the 10, and we're going to divide it by our pointer size default, which is 2 to the 4, or 2 to the 2, and that's going to give me 2 to the power of 8 pointers per block. All right. What do we do next? Now that we know how many pointers per block there are, we can figure out information about our files. So we could compute the maximum file size, but I'm going to tell you right now, we don't need to. So let's look at our indirect pointer block. So our one indirect. Now this is going to point to, so 2 to the 8, by the way, is 256. So it's going to point to 256 blocks of data are accessible via the single indirect pointer block. But what do those bytes correspond to? So let's take a look. So what we're going to have here is, you can imagine we actually have our pointer block. And we need this pointer block, so I'm going to draw it out. So here is my first pointer. My first pointer is going to point to bytes 9216 to 10240. We're looking for byte 10,500, so it's not here. So let's look at the next block pointed to through the indirect block of pointers. That one is going to go from 10,240 to 11264. Look at that. We found byte 10,500. It's here. Okay. Have we found out enough information about this diskette? Not quite, because if you look up here in the problem, we're going to start our write at 10,500 and we're going to write 1,000 bytes, which means we end at byte 11,500. And 11,500 isn't in this block. So, oops, that's the wrong color. The next pointer in the pointer block goes from 11,264 to 12,288. So we've now found 11,500. Do we have all the information we need, though? And the answer to that, again, is no, because after the write of 1,000 bytes completes, which it finishes at a byte 11,500, we then do a read, and the read starts at 11,500, and we read 1,000 bytes, which means it ends at 12,500. So we need one more of these. And this one is going to go to 13,312. So now I know which blocks each live in. And now I am ready, now that I've drawn this out and figured out where the bytes live, I can now solve the problem. So we have first to compute the number of reads and writes that happen from the seek. And the answer to that is none, because remember, seek doesn't actually touch the disk. It doesn't read the inode. It doesn't validate that the byte you are seeking to actually exists. All seek does is it's a system call that's going to cause the file descriptor table, the entry for your file, it's going to change the current file position to be 10,500. It doesn't validate it. In this case, we know that the file is very big, so we don't have to worry. Okay, so for our lseek, I'm going to make this a bit bigger now. And we're going to do this in a different color so that we can see this. So for our lseek, we have 0 reads, 0 writes. Now let's look at our write operation. Okay, we are going to write 1,000 bytes starting at 10,500 and ending at 11,500. So there's our write operation. The question is, how many reads do you have to do? Well, let's count them. I have to read the inode. I assume I already have the file descriptor, so I don't need to do the path to inumber translation. But I still have to read the inode because it's not in the inode cache. So read the inode. When I read the inode, I realize I want to read from byte 10,500, and so I then am going to read the direct or the indirect pointer block. And then I am going to read the data block corresponding to the start of the write. So 3 reads so far. And then I am going to read the other data block because you'll see the write is actually distributed over 2 data blocks. So I have to read both of those data blocks in. So in order to do this problem, I need 4 reads. How many writes do I need? Okay, we have to write 2 data blocks. I have to write the data block where the write starts, and I have to write the data block where the write ends, because it's split between 2. Remember that you can't do a partial block update. You actually have to read in the whole block, update in memory, and write the whole block back out. So that's 2 writes just to do the write, but there's a third write that's going to happen as well. The third write that happens is we just modified this file, which means we need to update the inode to indicate that the file has been modified. So there is actually 3 writes that happen. And at this point, I'm going to say that my caches now have the inode. I'm going to number these blocks. I have the pointer block for the indirect pointer. And I have data blocks D1, and I have data block D2. And that is within my in my cache at this point. And so now that my write has completed, I'm now going to do my read. We're only going to count reads and writes at this point that actually happen on the disk. So we're counting I/O operations. So my read is going to need the inode. The inode is in the cache, so we don't have to actually grab that from disk. I realize that I'm going to have to use my indirect pointer, so I need the indirect pointer block. But it's in the cache, so I don't have to grab that from disk. I realize that my write is going to start in data block 2 at 11,500, and it's going to end in data block 3 at 12,500. And so I'm going to need to read data blocks 2 and data blocks 3 from the pointers in the indirect block. Now, data block 2 is in my cache, so I don't need to read it from disk either, but data block 3 is not. And so I'm going to need to do 1 read from disk, and that's to get data block 3, and then I have to do 1 write. And I have to write the inode back to disk because I just accessed file data and I need to update the timestamp for last file access. So this is your answer right here. Let's use a nice highlighter. Let's color it pink for math. There you go. There's your answer. So this is a really fun problem because it gets you thinking about how does the file data actually correspond to those direct and indirect pointer blocks. So I really enjoy this one. I know most people don't, and at the end of the term, this is the number one question that people have is, wait a minute, how did you do that again? So play with it, and maybe you want to try doing your own read and write operations to see how can you actually figure out how many reads and writes there are. All right, so that's enough of that. What I'd like to do now is we're going to switch over to some other slides about designing your own operating system. It's kind of a lovely little wrap up to the whole course. So, suppose we wanted to design our very own operating system. How would we do that? There's actually lots of things that you need to consider before you can actually design your own operating system. One of the things you need to consider is on what kind of hardware is your operating system going to run? Is it going to run on the computer hardware that's sitting in front of you right now? Is it going to run on an iPhone or an Android-based cell phone? Is it going to run on a smartwatch? I've got a somewhat smart dumb watch sitting up on my desk here. It's from Sun2. So yeah, it doesn't answer your phone calls. It just tracks your heart rate and all that other kind of stuff. Am I trying to write an operating system for that? Am I trying to write an operating system for my toaster or my fridge? You have to think about what is the hardware you are going to be writing this for. Then you have to ask yourself, what kind of programs are you going to run on this? Is this a general purpose operating system for your home user? Or are you trying to write an operating system for your car? Cars need operating systems these days. You need a control system in a car to control things like the air-fuel ratios. You need to have operating systems to figure out what to do with boost. My car used to have an electronic boost controller, for example, that was controlled through the ECU. Now it has a manual boost controller. That's a long story. Let's just say my car's on its third turbo. So you have to ask yourself, what kind of hardware am I running this on, and what is the kinds of programs that are going to run on it? For something like a car, it might be things like controlling, writing software programs that are going to let you manipulate the values of the air-fuel ratio to give your car better performance or better fuel efficiency. For cars, the programs that might also run, especially if you've got like a modern car that has like backup or object detection, you might actually be having programs like detecting whether there is a grocery cart behind you, or are you too close to things? Like, are you too close on the side? Are you too close on the front to another object? Too close behind? Collision detections. So you have to ask, are those the kinds of programs you're going to run? Programs that need to be real-time operations? Or are you running things like, in my car, we don't have any of that stuff. We did install a lovely TV system for the kids, though. So the programs that run on our system are going to be Let's Play long plays of Zelda. It's a favorite in our car to watch. So is it going to play media? A general purpose operating system has to be able to run all kinds of user programs, from business kinds of applications to video games to web browsers. But you can think of, cars programs are going to be very different from consumers' programs on their home computer. And then if we think of the case of something like a smartwatch that doesn't do phone stuff, something that's just got a GPS and some basic biometric tracking, the kinds of programs that are going to run on that watch are very different. They're very simple programs. And you have to think about what kinds of programs are going to run on this operating system to help you design the operating system. Because you want to make sure that your programs run effectively and fast and securely. And the kinds of programs you're going to run is going to dictate how you implement some of those system call-like features in the OS. Question on Twitch, are these slides available somewhere? They aren't actually, but I will post them to Piazza. This is not a part. I'm not testing you on this. That's mean. It's the last day. I'm not testing you on this. But I will post them on Piazza for you. So another thing you have to ask is, who are your users? Just like you need to know what kinds of programs you're going to run, you need to know the kind of people that are going to actually be using the OS. If you're trying to write an operating system for, let's say, servers, like for Amazon, you know that the users, the people that are actually going to be using the operating system for the server itself, yes, I mean, people are indirectly using it, like home users through AWS, but they're really just running VMs. So if we're talking about the actual core operating system that Amazon servers are running, it's really only Amazon employees that are going to be using that and maintaining that. So we have to think about, who are our users? We also have to ask ourselves, how many users? Because if I think about my little Sun 2 smartwatch, then there's only one user. It's just me. So I don't need, the reason why you think about users is because knowing how many users there are and the kinds of programs and who your users are will determine whether you need to support multiprocessing or not. My little Sun 2 watch doesn't need to support multiprocessing because all it does is either do GPS tracking or heart rate tracking. It's very, very basic. Very basic. Things like a cell phone. If you know that the cell phone is really, really simple, then you know that you don't need to support a lot of multiprocessing. For the record, my first cell phone, my family, we were very, my husband and I, we were very resistant to the cell phone movement. We just didn't like the idea that people were always on them and they could contact you anywhere. And there was this, feeling that you had to answer immediately. So we resisted cell phones, but we realized they were important for emergencies, especially once we got a bit fancier of a vehicle. So we actually started out with something called a John's phone. And it's just a box with the number pad on it. And the address book was just in the back of the phone. There was a door, and inside the door there was a pencil and a little book of paper. That was our cell phone, our first cell phone. And you're probably thinking that was the 90s. No, that was like 2010. But see, knowing your hardware, knowing your user, the kind of programs they want, is going to help you dictate how your operating system is actually going to be designed. We also have to think about things like security. Does it matter to you? Let's suppose you were writing your very own operating system that you were going to run on some kind of Raspberry Pi board, and it's just like a Tinker Toy. Well, then I don't care about security because it's a Tinker Toy. It's not even connected to the internet. It's something I use to entertain my 2-year-old or something. Then we have to ask, does performance matter? For something like a little toy, performance probably doesn't matter. It matters for consumer general purpose operating systems, but not as much as it matters for something like a real-time car operating system. So if I was trying to write a new OS for my car, I'm not going to do. That's a really bad idea. My car's 10 years old. I'm just going to let it be for a little while. So if I was, however, designing an operating system for my car, I would obviously really care about performance and response times because I want my car, if it's starting to detect engine knock, I want it to respond to that immediately and adjust the parameters so that I don't end up destroying my engine again. Sorry, I like to use my car as an example here because I've modified my car a fair bit. And so, yeah. If you buy, a rally car or something like that, and you get it in your head that, would be really cool? Let's go stage 3 and rip the engine apart and modify it. So instead of having 305 horsepower, let's modify it so it's got 500. Just don't. It's not worth it. It's fun. Don't get me wrong. But you'll always be having engine troubles. All right, other things you have to ask yourself, is this computer going to be attached to a network? Because if you are going to be attaching your computer to a network, then you have to consider security a little bit more seriously than a computer that's not attached to a network. And you might be wondering to yourself, why would a computer not be attached to a network these days? Actually, I can answer that question. So my car is actually attached to the network. I have a little So there's a port under your steering wheel that you can plug things into. It's the OBD2 port. And I actually have a little Wi-Fi thing attached to it so that I can talk to my car's computer through the cell phone. I know that sounds weird, but it's kind of cool. But in the film industry, we actually have a lot of computing resources that we don't attach to a network. And the idea is if we're working on some kind of sensitive material that we don't want hackers to be able to access, then we simply don't attach the computer to the network. Solves that problem, right? Actually, it doesn't solve anything because most leaks that actually come during the production phases of a film actually come from the people working on the film. So that's a whole other story. So there's a comment on Twitter that says Fridge OS is cool because you can browse memes when waiting for the toaster to finish toasting. Yep, there's all kinds of crazy OSs out there. I don't think they care about performance in Fridge OS, and I don't think they care about security, but they are attached to a network. All right. So let's actually go back and talk about some of these in a little greater detail so you can see just how tightly integrated the design of an OS is with each of these things. So starting with architecture, which is one of the most important ones, is that what are you going to run your OS on? Is it going to be just one architecture? Because if you look at something like macOS, macOS is really only designed to run on Mac hardware. And it's not that you can't run macOS on other hardware like a generic PC. If you do that, though, they call those Hackintoshes. I did that once. I don't remember the context under which I had to do that, but I did have to do that at one point. It's not fun to try to get macOS to run on non-Mac hardware, although it can be done. So the question is, do you support only one architecture, or are you going to make your operating system portable and actually support multiple architectures? So if you think of something like the Linux kernel, which you can run on all kinds of different hardware, obviously there's going to be some significant differences to the design of the OS such that the Linux kernel can actually be compiled and executed on different architectures. So that's going to mean that they're going to have a lot of macros and a lot of, preprocessor flags in the code where it's like, okay, am I building for a PowerPC? Am I building for a Xeon processor? Am I building for an AMD chip? So that's just going to be for the compilation. And then from a device driver's perspective, the Linux kernel actually has device drivers for so many different things. Like the majority of that OS is made up of device drivers. The same is true, of course, for Windows. Now, for Windows, obviously, you don't get to compile it yourself because it's a closed source product from Microsoft. But if you were to look at the source code from Windows, you would see that, again, it does actually have a lot of drivers for a lot of different hardware. And you can run Windows, of course, on AMD. You can run it on Intel. I think you can run it on PowerPC. They might have at one point had a version that supported PowerPC. And this is actually an irrelevant topic because Apple now is talking about moving away from Intel chips and into their own, I think it's called M1 chip or something. That actually, I'm sitting here and I'm thinking, because PowerPC worked out so well for you. Why would you do that again? So if you're not aware of Apple's history, they actually didn't use Intel chips until the early 2000s, I think it was. And kind of before that, they weren't going through the most popular phase. There was a period where Apple almost died, I want to say, and I think it was the 90s. And then they switched over to Intel and they switched over to a Unix-based operating system. And things got a lot better. They had the iPhone and now they're super popular. And I think that they are going to risk going back into one of these unpopular phases if they go to their own chip. Because I'm thinking about this from my own perspective of I have a MacBook Pro. And if they switch that over to their own CPU, how do I, performance here? I know what an Intel i9 can do, but what can your CPU do? Where's the track record? Anyways, that's a rant. So we have to ask ourselves when we're designing this OS, is it for only one architecture, or do I need this to be portable and support multiple architectures and a large variety of devices? Obviously Mac OS, because it doesn't support a lot of different hardware options, doesn't usually support as many devices by default. All right. So as I was saying, if you're going to support, there's some advantages and disadvantages to both of these. If you're supporting a singular architecture, let's just support ARM. That means that your implementation is actually going to be simpler. Your code base is going to be simpler because it's not going to be littered with a bunch of preprocessor flags saying, okay, well, if we're on PowerPC, we have to use this particular instruction. And if we're on this other thing, then we have to use this particular thing. So your code will be simpler. It will be easier to maintain. But the longevity or the lifetime of the code that you've written comes into question, because if the architecture dies, then your OS dies with it, or you're going to be forced to actually overhaul things almost from scratch. Because if you do something on a singular architecture, you have the advantage of optimizing for that particular architecture. But if you're going to support a number of architectures, it's much harder to make those kinds of specific optimizations. And if you want an example of what I mean by that, if you've ever done any GPU programming, it's writing code for your graphics card, I prefer to use CUDA, which is for the NVIDIA ones, because you can actually tailor the code for your particular GPU, so you're getting the best performance possible. You can use non-CUDA based tools, and I don't remember the name of them anymore, but RapidMind, which got bought out by Intel, and I don't know the name of the product. It's a Waterloo startup anyways. But they actually had a general purpose tool to run things on your GPU, but that wouldn't have been as optimized. So a singular architecture support is going to let you really tailor your code to that architecture. But there's no portability. It doesn't live very long. I mean, look at MIPS. MIPS has kind of fallen by the wayside and replaced with things like ARM. Now, so there's pros and cons if we've seen there. With supporting multiple architectures, your implementation is going to be a lot more complex, and your code isn't going to be as easy to maintain, and it's also not going to be as optimized for any one architecture. It'll be generally good, but it won't be the best it could be for an individual architecture. So that's kind of the downside of it. The upside of it, however, is that your OS could actually live a lot longer, and it will probably be easier then to add more architecture support in the future. All right. So we also have to talk about abstraction, because remember, that is really what our operating systems are doing. A kernel is what stands between the hardware and the user, and its job is to abstract in a lot of ways. So we are abstracting devices, networks, file systems, processes, concurrency, memory. That's what OS 161 abstracts. Now the question is, if you're designing an operating system, what are you going to abstract? And what are the consequences if you don't abstract these things? So Temple OS is actually a good example here, because they didn't abstract all of these things. So just for the sake of discussion, what do I mean by that? So for example, in Temple OS, they didn't abstract the user programs from the kernel. Like, they didn't perform that isolation, which means the consequence is the user program can directly access the kernel's data structures and the kernel's API. That's a good thing and it's a bad thing. It's a good thing because it improves performance. It's a bad thing because it's bad for security. And it's bad for, oops, I accidentally overwrote something I shouldn't have. Then we have to ask ourselves, even in the design of the kernel, are we going to go for a monolithic operating system or a microkernel style OS? So monolithic is probably the most common. That's where we put everything in the kitchen sink into the kernel. So this is going to give you, the developer, greater control over the system and how it's used. It gives you greater control over device behaviors. You can hide it. So if you wanted to make a closed source operating system, you probably want to go the monolithic route. And in fact, if you look at all of the major closed source operating systems, they are monolithic. I think QNS is closed source. I'm not 100% certain on that. It is an oddball because it is a microkernel. So the advantages of a monolithic is that you have greater control, but the downside is that you have a very large code base, possibly billions of lines of code, and it makes debugging really, really hard because, I mean, you've seen how hard it is to debug something that's only like 20,000 lines of code. How hard do you think it is to debug something that has billions of lines of code? I don't even want to try. And yeah, microkernel, on the other hand, you have less control over the system because you have very little in the kernel. Excuse me. And the user is going to have a lot more control over the kinds of programs that are running. The advantage here, though, is you have a very small code base, which makes it very easy to maintain and patch, and it's very easy to fit it in hardware. So disadvantages are you have a little bit less control, but you also have a smaller, easier to debug code base. Then you ask yourself, should my operating system be real-time or not? This is actually a big question these days because we always refer to, operating systems are real-time programs, and yet we distinguish still between a regular OS and a real-time OS. And that, remember, comes down to response times. So in a real-time OS, we are actually making guarantees about the response times. Like, what is the maximum wait? And if you're trying to design OS, you have to ask yourself, do I need it to be real time? Do I need to guarantee that the responses to events happen in a short period of time? If you're writing something like an operating system to play games on your fridge, you don't need it. If I'm writing an operating system to run on my printer, I don't need it to be real time. So I use the printer as an example because one of my co-op jobs eons ago was actually writing printer drivers, and one of the other projects I worked on there was actually writing an OpenGL JIT compiler so that we could run Unreal Tournament on the LCD screen of a printer. I'm not sure why we were doing that, for the record. But it was fun, right? Again, not something we needed to be real time. But if you're trying to develop an operating system for your car, whether it's for controlling the engine parameters or whether it's for detecting, collisions with the outside world, you want that to be real time because you don't want to end up having your self-driving car hitting people as they cross the street. That would be very bad. This is actually why I don't think self-driving cars are going to take off for quite some time, is I don't think we're quite there yet. Too many people have gotten hurt so far. So if you are going to choose a real-time OS because it is something that you need, whether it's because you're trying to control robotics or you're trying to control car, you have to then discuss further what is an appropriate response time and what kind of guarantees are you going to make to your users or the hardware so that they can develop the programs appropriately. And then we have to talk about things like multiprocessing and threading. So how are you going to support this? My little Ubuntu watch, if I was writing an OS for this, I'm not supporting any multiprocessing because there's no reason to. It has a teeny tiny black and white LCD screen, and I don't really care if multiple things run at once. But and maybe if I was doing an Apple Watch, I mean, come on, how are you answering like the phone on something like that's like an inch or two in size? I don't get that. Maybe I'm just old. I don't know. But I wouldn't make the Apple's Watch support 20 processes at once. That doesn't make sense. Who is watching 10 YouTube videos on a screen that's 1 inch in size? Okay, I've never actually used an Apple Watch, so I don't know if you can even watch YouTube videos on one. But who would? I'm going to sit there like this. Yeah, no thanks. So let's suppose you are going to support multiprocessing. Then you have to ask questions as how are you going to implement that? Are you going to just do cooperative concurrency, where we are going to rely on the good behavior of the program to have a context switch, so blocks, terminates, and voluntary yields? Or are we going to do something a little bit more modern and actually do preemptive concurrency? Ugh. So And then you have to ask yourself, is there a maximum number of processes I'm going to support? So if you look on a lot of computers, I think the maximum PID on most is something like 99,999 or something like that. Or maybe you think that's too many because maybe you are writing an OS for a cell phone. And the concept that you could have 99,000 apps running at the same time is ridiculous because you don't have enough memory to support that, number one. And number two, your CPU couldn't do it either. And besides, who's watching that many YouTube videos at once? So maybe you want to have fewer supported number of processes. And then you have to ask yourself the question, based on the maximum number of supported processes that you have, are you going to be permitting the reuse of PIDs? So let's suppose that you technically make your max PID 99,999. Does that mean that's how many processes that you can have running, or is that simply the maximum PID? If you are going to reuse PIDs, how do you reuse them? And what actually comes into this discussion here, which is kind of interesting about talking about reusing PIDs, is you have to ask, for how long is the operating system actually going to be on for? Because if you reboot the operating system, you could actually restart your PID count back at 0 again, or back at 1, however you want to implement it. So if you actually intend to write an operating system that has the ability to run for decades without being rebooted, then you're going to need to make sure that you have a lot of PIDs available and that you're reusing them effectively. So something like OpenVMS, which has been reported to run for over a decade without being rebooted, you can imagine that it handles this really well. And then we have to talk about, separation between the kernel and the user. So are we going to actually separate them, or are the processes actually going to be permitted to access data structures and APIs within the kernel? Now, most people, other than TempleOS and early versions of Windows, aren't going to let the user program actually execute any kernel material. So if we're not going to let the user program do that, then we have to ask ourselves, what about the process management system calls? Which ones are we going to support, and how is that actually going to be executed? So are we actually going to have to raise an interrupt? Am I going to have one singular kind of interrupt for a system call, or am I going to have different ones? And what kind of arguments do I have to pass through the trap frame? So there's lots to think about there. And then you might be thinking to yourself, if I want to improve performance, what kinds of shortcuts can I take in order to improve the performance of system calls? So is there anything that I can skip due to this being run on a particular architecture? Lots to talk about. So, and then we have to talk about, just because you can support multiple processes, do you let those processes have multiple threads? Some of you may have noted in OS 161 right now that we actually don't support multiple threads per process. And the only time you actually had a multi-threaded program was on assignment 1, when you were running code in the kernel. We don't have a user level thread library, which means each process in OS 161 can only have one thread. So if you wanted your processes to support multiple threads, you actually need to design that into your operating system. So your process would need to have a thread array. And then when you are calling proc destroy, you actually have to terminate all of those threads. And it comes in really interesting is when you have something like wait PID and multi-threaded processes. Because it's one thread of the process that called wait PID. What if that process has 99 other threads? Do they all also have to block for wait PID? Or are you going to make it just that one thread of the process block for wait PID? And I was doing some reading probably a year or two ago, so my memory's a little hazy, but it seems that different operating systems actually handle that differently. So there's lots of interesting interplays between the system calls and whether you support multi-threading, and it's fun. I mean, another discussion here is how does fork behave on your system? So if your process supports multiple threads and you fork, are you going to create a duplicate process that actually has all of the same threads doing all of the same things? Or are you creating a new process that only has the one thread that actually called the fork? How do you do that? What's the intended behavior? That's your choice. That's your choice. You get to choose. And then you get to communicate to your users, this is the behavior of fork. Then you have to ask yourself, are processes able to actually communicate with each other? So are we going to actually let the processes share an address space like in Temple OS, which obviously is a bit of a security leak? Or are we going to force processes to communicate through inter-process communication mechanisms? Are we going to offer a message passing system call to let one process talk to another? Or are we going to force processes to communicate with each other via files or shared memory spaces? By the way, that's actually one of the easy ways to get two processes to talk to each other is to have them both read and write the same file. Now, obviously, that's going to introduce a lot of synchronization issues, but that's a really easy way to do it. All right, a comment on Twitch. Is there a way to know for certain that the multi-threading processing has no race conditions? There is a statistical way, but there is always a chance the next test run exposes a race condition. So 343 was a really long time ago for me. I think I took it in 2003. It seems to me there are some mechanisms by which you can prove that certain kinds of code works, like it doesn't have a race condition. But the more sophisticated your code gets, the more that the chances of the outside world has to interact with, I don't think it becomes as simple to prove one way or another. And, on this topic of talking about, is there a way to write an OS where you can prove that there's no race conditions? So Google actually wrote this code, this little analysis program to actually go through kernel code and determine if there were any deadlocks or race conditions. And I think for the Linux kernel alone, they found over 300 mistakes. 300. So what I'm trying to convey to you here is, I think for some simplistic problems, you would be able to actually prove it on pen and paper. But as you make more and more complicated systems, I don't think it's so easy to prove it or possible. So you have to rely on either statistically it works or we believe it works based on some logical arguments that may not necessarily constitute a full proof, but based on principles and practice. It's complicated. By the way, there's like a reason we have a full course dedicated to this topic. And if you're asking, should you take 343? In today's world, I think it's absolutely critical you take 343 because pretty much everything we do involves concurrency and synchronization. And Peter Beer is absolutely wonderful for 343. He taught me 343 and the 800 level version of it, which I don't remember the course code. He's a wonderful, wonderful instructor for that. Professor. So now let's talk about scheduling. So if we do support multiple processes and we do support multiple threads in some way, how are we actually going to perform the scheduling? So are we going to have priority-based scheduling where we actually let some threads have greater priorities than others? Then we might do something like completely fair scheduler from Linux or multi-level feedback queues, which of course, even then there are implementation details. For multi-level feedback queues, for example, how many queues? Solaris has 6. I think Windows has 10 now. They didn't always have 10. They used to have fewer than that. Or are we going to use something like the lottery scheduling system, which is one of my favorites. It's so fun. So for those of you who have never heard of the lottery scheduling system, the basic idea is you assign a number of tickets to each thread based on their priority. So if you have a higher priority, you get more tickets. And then on a context switch, you randomly draw a ticket. And then the idea is, statistically speaking, we expect that higher priority threads will get to go more often. So that's kind of a fun one. It's actually pretty easy to implement too. Or are there other kinds of scheduling algorithms? Which one are you going to use? And if you're implementing a scheduling algorithm, what is your scheduling quantum that you're going to use? So if multi-level feedback queues, you have to set several. If you're using completely CFS, then you have a singular scheduling quantum. What's it going to be? What is an appropriate scheduling quantum? Well, that's going to come down to the architecture and the implementation of the OS. How much work has to be done in order to perform a context switch? Because we don't want a context switch to trigger while we are doing a context switch. So this actually comes down to the design of the system, and it comes into play about what is the architecture you are running on. And then we have to talk about virtual memory. So are you going to use it? I know earlier versions of Windows and DOS actually didn't, but most operating systems these days still use virtual memory. So if you are going to use virtual memory, what are you going to do? So are you going to support preloading of the address space like OS 161, where we load the whole program into memory first? Or are you going to do on-demand paging, where you only load the parts of the program when you need them? And once you've decided on how you're going to do the program loading, then you can also decide at the same time, are you going to use segmentation? Are you going to use paging? Are you going to use a combination? And it's not purely your decision, because you have to go back to the architecture decision. And the architecture may actually dictate which virtual memory implementation you have to use. Because if your architecture does hardware managed TLBs, then you are going to have the page table format dictated to you by the hardware. This is why there's a lot that happens with the design of an OS. So first off, with choosing which method, you have to know what is your architecture support. You need to know how much memory is going to be available. For the record, if you buy a computer and you think to yourself, okay, I'm just going to, as RAM sticks get bigger and bigger, I'll just keep upgrading it. Well, actually, a lot of systems actually have a maximum amount of physical memory you can install. And it's not like even close to the theoretical maximum. So I remember years ago when I bought my 17-inch gaming laptop, it has like 4 RAM slots. And even though I think it had 8 gigs of RAM. And even though you could purchase much bigger pieces for it, I want to call them SODIMMs or things like that, but that's not what they're called anymore. Even though that you could buy bigger DIMMs for them, there was a maximum amount of memory the system actually supported, and that was actually a hardware limitation. So you have to take that into consideration for your OS. Is there a maximum amount of memory that the architecture supports? For MIPS, for example, has some limitations on that. And it even has some limitations as to how the virtual memory is arranged. And so you have to know these things. And then after you've figured out what your hardware demands and what you can get away with in the kernel, then you have to ask, okay, how many users, how many processes? What's the size of the program address space? Is fragmentation going to be a problem? If the address spaces are going to be really, really large, then like to the point where they're maxing out virtual memory, then I don't want to use multi-level paging, because that's actually going to cause a problem. Because then my page table will be enormous. So you really have to think about these things when you're implementing something. Then, of course, there's the discussion of devices. So what devices are you going to support? And it's not just what devices are you going to support today, it's what devices are you going to support tomorrow. Because if I were to develop an operating system right now, and I develop it such that I have device drivers built in for the computing equipment sitting in front of me, so then I would have a device driver for my camera, a Logitech Brio. I would have a device driver for this microphone, which is a Yeti X. And I have a device driver for this crazy monitor to my right that you can't see, which is actually an LG ultra-wide 4K HDR screen. It's awesome. It's like 9,000 pixels wide by like 2,160 pixels tall. It's awesome. It's like having 2 monitors in one. So I would write device drivers for the equipment sitting in front of me. I'd have a device driver for this. But that doesn't tell me what I'm going to use tomorrow. Because maybe tomorrow I decide to replace this camera with something different. Maybe I go buy a 5D Mark III and I use that instead. So when you're building an OS, you have to ask what devices are you actually going to support, have built-in support for, and how are you going to make it so that new devices can be added easily in the future. So are you going to make things plug and play, where you have every driver under the sun built into the kernel, so the chances of the user plugging a device in and it just working is almost 100%. And if it's not something you recognize, is the operating system actually going to go out and find the driver on the internet and install it for you? So do you want a plug and play style system, or are you going to require your user manually install the drivers themselves? I'm going to tell you the truth. When it comes to things like Linux, I like Linux to be able to find the driver for me, because there's often many options. And if the kernel is fine choosing the one for me, I always assume it's choosing the right one. But for Windows, I want to choose the driver myself. And there's actually a history behind that. So Microsoft used to offer their own NVIDIA driver, not one provided by NVIDIA. They actually used to have their own NVIDIA driver, and it was awful. It didn't work properly. Like, it didn't give you access to the full features of your card. It crashed a lot. It was really, really bad. And so Microsoft's plug and play system would by default use their own provided NVIDIA driver instead of using NVIDIA's proper driver. So for Windows, I actually prefer to install my own drivers so that I'm ensuring I get the right one that was actually designed by the company for the device. Because I don't have, based on this fiasco with the NVIDIA drivers from Microsoft, I actually don't have faith that all of the drivers they offer actually work anymore. But for other OSs like Linux, I tend to just trust it, actually. Maybe I shouldn't, I don't know. And then you have to also ask yourself, so that's how to install the device. You have to ask yourself too, like, is the device driver going to run in kernel mode, or is it going to be more of a user ran thing that uses system calls? Are you going to support legacy devices? So a lot of modern operating systems, these big monolithic kernels like Windows and Linux, the Linux kernel and Mac OS actually support a large number of legacy devices. Like they support Dvorak keyboards. I know that's not legacy, but most people don't use them or have even heard of them. They also support things like Sound Blaster 16s, which I had in the 90s. And they'll support Riva TNT2 cards, which I had in the 90s. They still support it. Do you want your operating system to actually support legacy devices? I know if I were to actually create an operating system today, I probably wouldn't support these things because I think it's just adding to the bloat. And if I'm writing an OS for myself, I know that I don't have this hardware because I try to keep myself up to date. You also have to discuss how are you going to communicate with the device registers. Remember, we talked about 4 different techniques for actually sending data in between the kernel and the device. So there was program-controlled I/O, there was DMA. Then we also had port-mapped I/O and memory-mapped I/O. So there's so many different ways that you can do it. Which ways does your OS support? What ways does your hardware support? Because maybe you don't have a DMA controller. So that's automatically going to knock DMA off your list. Maybe your hardware doesn't support port mapped I/O, which would be very weird, but maybe it doesn't. So then you're stuck using memory mapped I/O. So you can see here how architecture is very tightly tied to this design process. And then, of course, there's file systems. So which file systems will you support? Are you going to support a variety of different file systems? Are you going to support a variety of different ways that you can attach secondary storage? So are you going to have a virtual file system that will let multiple file systems be presented as one? Are you going to allow that or not? And if you do allow it, how are you going to do it? Are you going to do Unix-style mounting? Are you going to do a 2-part naming system like Windows? Or are you going to invent your own thing? It's the beauty of writing your own OS. You can do whatever you want. But you have to do things based on your users and your architecture. You don't just start designing an OS or writing an OS with no plan, right? That would be kind of weird. And are you going to use things like caching? So are you going to actually use an inode cache and a data block cache? Are you going to utilize some hardware for that cache? So for example, now we have things like Intel Optane, which let us actually create really large inode and data block caches for secondary storage on SSD-like memory. So does your OS support that? Obviously, if you want to support this hardware, then your kernel actually has to know about it and be able to use it. And then, of course, if you're designing, which file systems are you going to support, it comes down again to what are the users using your OS for? Is this just some kind of database OS? Well, then that's going to dictate the kinds of file systems you support. Or is this like an archiving thing? Or is it general purpose? Are you anticipating lots of power outages? That's going to dictate whether you want journaled or not. And then you have to talk about networking. And I know this is something we don't talk about in this course, but are you going to support networking? And if you're going to support networking, how much of that is actually going to reside into the kernel? Right now, the majority of the networking implementation actually does reside in the kernel. So if you're familiar with the 5 or the 7 layer models, most of that actually does live in the kernel. And you use system calls and you create sockets to actually interact with the network. But pretty much everything else lives in the kernel. And then you have to ask yourself, so if a lot of this is going to live in we are going to do networking, what is the operating system? What is the kernel going to handle for us? So that's some good spelling there. Is the kernel going to do a DNS cache? So for those of you who are unfamiliar with networking, a DNS cache DNS is a domain name. Oh God, I hate acronyms. Domain name service. And what it does is it maps, how we have directories to map paths to iNumbers? Well, DNS is mapping URLs to IP addresses. So does your operating system have a kernel cache for a DNS? So does your kernel keep a table of all of the different URLs that you visit and what IP addresses they map to? So that, because right now, if you didn't have this in your kernel, what ends up happening is you actually have you send a request with the URL, and before you even that request gets to the website, like let's say you're going to Amazon, before that page even loads, we have to first ask your network service provider, hey, what's the IP address of Amazon.com? So there's actually a ton of different messages that get sent before we actually ask Amazon to give us the page data. And one of them is mapping Amazon.com to its IP address. It's more complicated than that because obviously Amazon has more than one IP address. So sometimes you might actually, in your kernel, have a built-in DNS cache. So you don't have to ask an outside source for that. And I know sometimes if you've got a nice router at home, your router might actually have its own DNS cache built in, which is kind of nice. But maybe it doesn't. But your operating system included. And then we have things like NAT tables, which is a network address translation table. And what that does is it's going to, well, think of it this way. Have you ever noticed that it doesn't matter which home network you are on, the IP addresses are always like 192.168.1. whatever? Have you ever noticed that? Like whether it's your house or your parents' house, that's your home network IP addresses? It's because those are local IP addresses. So some of the IP range is actually reserved for local network use. And then when you actually go out to the real world, you only have one IP address that's assigned to you by your network service provider. And what happens is your home IP addresses get mapped to that. And then that table does the translation between your world view and your LAN view. So it's kind of cool. And then we have ARP tables. Again, this can be a part of your kernel to improve the performance of networking. And what an ARP table does is that's a lower level ID for network devices. That's the MAC addresses. So it's saying An ARP table will know which, how to access each of the different physical devices. There's all kinds of these different things, and we haven't talked about any of them, so I don't expect you to know. And then, so all of these different tables and caches your kernel can have to improve the speed of networking. And then your kernel could also have things like packet filters. So firewalls can be built into your kernel. Are you going to do it or not? You don't have to, because you can actually have external devices support that. There's a lot to designing an operating system. It's not an easy thing. And then on top of all the lower level stuff, you have to ask yourself, is this operating system going to have a UI? And if it is a UI, is it going to be fully integrated into the kernel? Or are you going to, in Linux land, or GNU Linux land, are you going to let people choose their own desktop UIs? Are you going to have shells and terminal support? How are you going to handle the performance of this? Are you going to have it built right into the kernel so it's super fast? Is it going to use system calls? How are you going to implement that? If this is an operating system that I'm designing for my car, I don't want a UI. I don't need a fancy UI. I need like basic terminal support, command line support. I don't need a fancy point and click UI. But if I'm building something for like a tablet, then I obviously need a good performing UI. And then there's the utilities. So that's the kernel design. What utilities are you providing? So the kernel ABI, the application binary interface, what are you providing by that? That's so the user programs can actually know how to interact with the kernel via system calls. What kinds of programming libraries? Do you even offer any, like standard libc? Are you going to have things like task managers to set priorities of processes and find ones that have run away and terminate them? Are you going to have packet sniffers? Packet sniffers, you've never seen those? Packet sniffers, this is one right here. This is called Wireshark. So let's take a look at Wireshark. Oh, I don't think it's going to like me right now because I am on Wired. So let's go Wired. Let's go with, I don't know. Okay, it's probably this Belkin one. Okay, yeah, it's the Belkin one. So let's go with that, and then let's there we go, packet sniffing. What did I just do? These are the packets that are running around on my home network right now. So cool, right? So I can actually sniff all of the packets floating around on our network. Is that going to be a utility that you offer as part of your operating system? Or are you going to offer that ability? Or are you not going to offer that ability? You don't have to. I mean, obviously, like, so that's Wireshark. You can download. That's a really cool tool. And then you have to ask, like, what kinds of network or device configuration tools will you offer? Are you going to make that easy for the user or hard for the user? System monitors to monitor temperatures and fan speeds, documentation and support. Obviously, if you're going to create an operating system for someone other than yourself, you need to have documentation and you need to have support for it. Like forums. Maybe if you're a big company, then you actually want to have like a call center. A lot of work goes into creating an OS and a lot of people. So yeah, Temple OS. So we can go through these. I don't really want to do this. We already talked about Temple OS, but very briefly, they chose to support multi-cores and they have preemptive concurrency sometimes, but they also have, they originally only had cooperative concurrency. They decided for security not to do rings of security. They decided everything runs in kernel privilege, which means no system calls, threads only need one stack, but there's no protection or security. I'm just looking at the time here. We're over time. So they have a single address space. So I'm not going to go through these slides. I'm going to let you actually go through these on your own. I will post them though. But just to give you an example of how interesting designing your own OS is. So that's it for today. That's it for the course. I hope that you have learned something. I hope this hasn't been a horrible online course experience for you. We welcome your feedback. You're welcome to email me directly or use the evaluate system. We want to create the best experience for you and for students moving forward, as there's going to be some more online terms coming. I hope that you have a safe holiday season and you continue to stay safe and healthy. And maybe we will run into you in person in the future sometime if you don't graduate before this is all over. So we will see you later.
Hello, I'm a Mac.
And I'm a PC.
Whoa, what happened to you, PC?
Kids happened. I was bought for a home. Now I have to make movies and blogs and listen to music every night. I'm crying myself to sleep mode.
Sorry about that.
You were made to stimulate 10-year-old brains with your iLife jazz. All I want to do is balance their checkbooks.
I don't think 10-year-olds have checkbooks.
No checkbooks, no inboxes, no employers, just wild imaginations. I have to go listen to some emo. Ugh!